Hi, I'm Emily Sledge, and we're going to be talking about geometry here. And quick, without thinking about this picture too much, what's the first thing that pops into your head about what you're seeing there? How would you describe that to someone else? And if you're like most people, you'd describe it as, well, there's this circle and there's this right triangle inside of it. That angle at B looks like a right angle. And if you know a little about the rules of geometry, you may recall a rule about inscribed triangles in a circle. And you may know that there's a rule that if there's a right triangle inscribed, that hypotenuse will be equal to the diameter, which also looks to be true here. AC looks like the diameter. So one of the points of this exercise is you're greatly helped by having a picture of what they're asking you about. Unlike algebra, this is a little bit more visual realm. The flip side of that is your eyes can deceive you. So unless the GRE told you in words that the angle at B is actually a right angle, or they told you in words that AC is actually the diameter, you can't trust the picture to that level. Just because it looks like it is doesn't mean it isn't. It doesn't mean it's true. So that said, most of the time on the GRE, if there would be a useful formula that you could use, they will give you enough to tell you it's okay to use it. So the point is, if they give you a picture, redraw that on your paper, and then also check the words that go along with it to make sure what you know. So if you are going to make inferences on the GMAT, so based on the fact that AC is a diameter, you can infer that the angle at B is a right angle, and vice versa. You'd have to know your rules and formulas. So that's the downside of geometry. You have to do a fair amount of memorization. And that said, there's probably close to 40 big rules that you need to know. But of those, I would say some of them are derived from others. So if you look at just the fundamental rules from which others are derived, you're looking at about 12 main rules. So I highly recommend that as you read rules and formulas, you create flashcards for each of them. You also think about how one rule can be derived from another. Great way to group your flashcards as well. So our general approach on paper will be to draw the figure that you're given or redraw what's given on the screen. Some geometry problems don't have a figure on the screen. There's just words describing a figure. For example, they could tell you in words that there is a triangle inscribed in a circle. Go ahead and draw that on your paper. And add any other information that's from the text. So typical things to find are lengths, labels, degrees. One line is parallel to another. These lines are perpendicular, etc. Draw your picture bigger than you think it needs to be. With all those labels floating around, things can get really messy. Don't worry about wasting scrap paper on this. It's a good idea to keep your eye on where you're going. So a big old question mark next to the length that you're looking for, or a circle around the angle that you're looking for. Anything that signals to you what you're aiming for. You may not have to label every last thing on a diagram in order to get, the answer to the question. So invariably, you're going to need more than just the information given. You're going to have to infer from one label to label something else. So you need to know those rules, and you may even have to set up some equations to kind of solve for other measures in the diagram. All right, so let's proceed with the goal of running across and reviewing as many rules as possible. That's kind of the goal for this section. One other thing I should note is that as I throw problems up on the screen, those of you who already know the rules will probably move more quickly than those who are struggling to remember them, and that's okay. But to make this user-friendly, instead of putting a standard time on the clock for each problem, I'm going to put up a problem and then ask you to pause the recording. I'll give you timing guidelines. I'll tell you have up to this amount of time for each problem. but it's up to you to time yourself. So if you don't have a timer handy, you may want to pause the recording now and go get one. All right, this one we won't do on a time delay, but I will pause here as you think about whether this is a legal triangle, and maybe more importantly, think about why or why not. All right, you may be checking this out with Pythagorean theorem. If so, you're going back to an old favorite, but there's nothing here that indicates this has got to be a right triangle. There's another more general rule about the side lengths of a triangle, and it's called the third side rule. It's a lot simpler than Pythagorean theorem, actually. It goes like this. Any side of a triangle has to be less than the sum of the other two sides or greater than their difference. I find that's a mouthful to remember. I like to remember it this way. A side of a triangle, take the sum and the difference of the other two sides, and those are the limits for the third side. Okay, so let's look at this. Here, 2 is exactly equal to the difference of the other two. So it can't be equal to the difference. It has to be greater than the difference of the other two. And visually, it helps to imagine, I think, these as like ruler segments. This one's literally 2 inches long to scale, 7 inches ruler segment here, and a 9-inch ruler segment here. And imagine hinges here. So these two can kind of swing up or down. What would it take to make them match or match up, meet here? Well, 2 and 7 are exactly 9, so they'd have to lay down completely flat in order to touch their ends. And then what we're looking at is really lines stacked on each other, not a triangle at all. That's why you need one of these to be longer than that in order to, bump up that corner of the triangle, make these meet up here, as opposed to right on this line. All right, so that's kind of a visual proof of that rule. Let's put this into action. Here's our first little set, and again, I'm not going to put a timer up for you. You will time yourself. Pause the recording, but you can give yourself up to 4 minutes on this one. Don't take longer than that. Come on back when you have 2 answers written down. And if that's at the 4-minute mark, guessing is encouraged. All right. Okay, so welcome back, and let's look at the first problem, the top one. When given 2 sides of a triangle and asked about the third, that says use the third side rule, especially if they don't give you any angles in the triangle. You're not expected to use Pythagorean theorem, obviously. So we've got 6 and 9. Easiest way to go is always take the sum and take the difference of the 2 sides that you're given. And those are your limits for the third side. All right, so AB has to be greater than 3 and less than 15. So 3 is not a valid answer. If you picked 3, you included that limit. This is definitely a greater than and less than situation, not a greater than or equal to type of situation. So 3 is not possible. If you multiply out on your calculator, 9 root 3 is more than 15. Approximating would be okay to do also. 1.7 is the approximation for root 3, and that'd be close enough to eliminate that one. In the bottom problem, we've got one big triangle kind of split into 2 triangles. As you draw that on your paper, you might not even need to write the letter X on the diagram. Why? Because you're given that in number terms. So as you redraw on paper, might as well just put that on your drawing. Likewise, 3x has got to be 3 times 35. So you know that in number terms. And with the yellow dot there, I've marked the angle that we're looking for, PQS. It's worth briefly reviewing how they call out angles on the GRE. Literally trace your eye from P to Q to S. And so what that means is Q, the letter in the middle, is always where the point of the angle is. Okay. Here they can't just call it angle Q because there's two of them there. They really have to specify that it's this one. And the PQS does that. The other angle would be called SQR. All right, so this is the one that we're looking for. And there's two rules on triangles and angles and lines that have to do with the number 180. Most people remember that the sum of the angles in a triangle have to add to 180. And you may also remember that angles that add up or form a line are also equal to 180. So that means these two angles have to add to 180. Put those together, and we see that the difference here must be 75. 75 and 35 give you 110. Back that out of 180, and we're at 70. The answer is D. Now, kind of a combination of those two rules about lines formed to 180 and triangle angles summed to 180 is this rule, that exterior angles of a triangle, so if we look at triangle PQS, this 3x angle is an exterior angle. You create an exterior angle just by extending one of the sides, and it's the outside angle that makes. The exterior angle is equal to the sum of the two opposite interior angles. So you could have set this up as 3x equals x plus question mark, what we're looking for. And that means we expect our answer to be 2x. Right? X plus 2x would give us 3x. And you could go to 70 from that. 2x is 70. All right, so that's an example of, you could either use two rules or you could use like the fancier hybrid of those two rules. But there we just reviewed three rules. All right, this is a QC question, so the standard time for this is 1:15. Make that your goal as you pause and time yourself. All right, triangles and also a rectangle mentioned here. So that's probably the first thing to note. There is only one angle labeled in the figure, but there's the implication of other angles. So if they tell us in quantity A that it's a rectangle ABCD, that means that each of these angles is 90 degrees. And from that, we can infer that this one is also 90 degrees in this triangle. These are two angles that form a line. So what are some things you can trust about the figure? They tell us it's not drawn to scale, but AE, this line, horizontal line, looks straight. The GRE will never play sneaky little tricks on you like, oh, there's a microscopic bend. This is actually an 89-degree angle here. No. If it looks straight, you can trust that it's straight. So if this is 90 degrees, this is 90 degrees. All right, so what that means is that triangle on the right is a 30, 60, 90 triangle. It's a right triangle. And that's a special triangle that has known side ratios. So it's always side and then root 3 times the shortest side. Then this longer side is that side times root 3, and then the hypotenuse is always 2 times the shortest side. So here, our shortest side is 2. This will be 2 root 3. This will be 4. All right, we're getting somewhere. And furthermore, with the whole rectangle, if you're looking at half a rectangle, you can split it a couple different ways. You know, think about the ways to cut a sandwich. You could look at it as, 2 rectangles of equal size. But here, since we're already thinking about triangles, it makes sense to cut it like this. So what we can really do is compare triangle ACD to triangle CDE. And the quantities become a lot easier to compare at that point because you're using the same formula. So it's 1/2 base times height for the area of a triangle in both cases. And the heights of these triangles are equal. The height is 2, line CD there. And so really what we're ultimately comparing is just the bases of these triangles. So again, that approximation of root 3 would come in handy. Quantity B is equal to 3.4. B is the answer. All right, a little bit of a word about circles before you do some problems on your own. The main thing about circles is that all the formulas are so similar. Every single formula about circles has a radius in it. So that implies that like radius is the most useful thing about a circle, but really anything that you're told about a circle is useful because you can use it to get to the radius. From the radius, you can get everything else. And that's what this problem is about. If you're given an area of 49 pi, well, that means area is pi r squared in general for a circle. And so set that equal to the specific area you're given, and you can use that to solve for r. R must be 7. And if that's the case, circumference is 2 pi r. These are formulas just to memorize. And so the circumference is 14 pi. I find that sometimes people get those two particular formulas about circles mixed up. I think maybe the fact that there's a pi, an r, and a 2 in both of them is what does it. So if that happens to you ever, fall back on the idea of units. When you square inches, you get, an area kind of measure. So you do want to be squaring radius, which can be measured in inches if you're solving for area. But you don't want to be squaring r if you're looking for a linear measurement. Circumference has just r by itself, not squared, because circumference is in inches and r already is. All right, here's a circle problem for you to do on your own. Take up to 2 minutes on this one. Pause the recording, come on back. Wow, talk about nested shapes. We've got a circle within a square within a circle. So another thing that you can trust about GRE diagrams is that if lines look like they intersect, you can trust that they do. So in other words, you can trust that these lines come to a corner here. Likewise, if it looks like that corner lies right on the circle, it does. If it weren't exactly touching, that would be drawn more dramatically as a gap. Okay, so you can trust that this quadrilateral is inscribed in the outermost circle. Now, I said square a minute ago, and it's not actually in the text of that question that that is a square. Think for a moment about how you would know that's a square. And that's where that inner circle comes in. One thing we know about a circle is that it is the same dimension across no matter which way we go. As long as we're measuring through the center of the circle, we've got the same diameter everywhere. It's not like an oval shape where it's uneven depending on which direction you measure. So we know that this diameter is the same as this diameter, and likewise we can trust that these are inscribed because it looks like it touches. And so that means height and width of this figure are the same. Okay, we're going to use all of that. So we're given the innermost circle area. Use that pi r squared equals pi formula. So pi r squared is what an area always is. This particular area is pi. We set them equal. That means the radius must be 1 here. And so the diameter is just double of that, and there we've labeled the 2. Okay, so that means, we've already kind of covered, that means that this square has a side of 2. And a good rule to remember, another good one for a flashcard, is that the diagonal of a square is always the side length times root 2. You can get there from Pythagorean theorem, because it's basically a 45, 45, 90 triangle when you split it by the diagonal. Square 2, you get 8. Take the square root, and that's equivalent to 2 root 2, but much faster to just memorize this. And that diagonal turns out to be the diameter of the big circle. So if that's 2 root 2, the radius of the big circle is just 1 root 2. Plug that into the area formula again. So the area of the big circle is 2 pi. C is the answer. Another thing you'll see with circle problems is sectors. And sectors, you can think of, cutting a pizza into slices. Sectors are segments of are areas of a circle that come to a point at the center of the circle. So that should probably be labeled, and in a typical GRE problem, this would be labeled and you would be told that this is the center of the circle. And the rule about sectors is you always look at this angle. So if you wanted to slice a pizza into equal slices and everybody got 60 degrees worth, how many slices would you get out of the pizza? Well, a whole circle is 360 degrees if you go all the way around. So 60 would go into that 6 times. Literally what we're looking at here is 1/6 of the pi. And so various questions can be built off of this. They can ask you for the area of that sector, which would just be 1/6 of the area of the entire pie. Or they could ask you about the crust, the arc measure from A to B, and that would just be 1/6 of the circumference. It's a pretty handy rule there. You'll find that useful on these two. Again, they're QC questions, so aim for 2.5 minutes on both together. Pause and time yourself. After making sure you have 2 answers written down on your page, let's discuss. So first, a word about terminology. Minor arc QR, minor arc. What that means is the short way around. So this curved piece is the minor arc from Q to R. There's another arc, and it's called the major arc, and that's the long way around the circle from Q to R. All right. Another way to call out that major arc would be arc QPR. So kind of like angles, you trace that path. All right, so we want this short one. And from the previous rule slide, we know that we need to find this central angle to figure out, what fraction of the circumference are we dealing with here? This isn't labeled, so we're going to have to get there. There's a couple ways to do so. One is you could say every line drawn from O, the center of the circle, to some place on the circumference of the circle, it's got to be a radius. So based on that, the radius is 9. This one was given to us, but we can label the other 2. These are radii also. And if you turn your attention to this side triangle, notice that it has 2 sides that are both equal to 9. A rule about equilateral triangles, those that have 2 equal sides, is that the angles opposite those equal sides are the same. So that means that this angle up here, PQO, is also 30. And angles in a triangle have to add up to 180, so this would be 120. This angle would be 60. And we've got our central angle, 60 degrees. Another way to go is to draw this line here and refer back to that rule that we used at the very beginning of this segment. This is a triangle inscribed in a circle, if we look at the overall triangle. And so that means this total angle at Q has to be a right angle. And now what we're looking at is a 30, 60, 90 triangle. And we've got 18 as our hypotenuse. Half of that is our short side. And now we're looking at a 9, 9, 9 equilateral triangle. Another way to get that this is all 60-degree angles in this triangle. Okay, so central angle is 60. And that's 1/6 of the circle overall. Use our diameter of 18. 18 pi is then our circumference, or plug into 2 pi r. And so that means minor arc QR is 3 pi. Comparing that to pi squared, I think, is a little easier if you realize that's pi times pi. So it's really, is pi bigger than or less than 3 pi? And quantity b is greater because pi is greater than 3. In other words, we have more than 3 pi over here. All right, so that one was a pretty challenging problem compared to the other one. I think the other one's a little bit easier. This one is about keeping track. So again, we've got that minor arc language. We've got minor arc PR and minor arc TS. If I were drawing this on paper, I would highlight that somehow and capture what they tell us in comparative terms. So we know the one on top is longer and the one on the bottom is shorter. And the implication of that is that the central angles correspond. So to have a longer arc, you'd have to have a bigger central angle. To have a shorter arc, you'd have to have a smaller central angle. And notice that's the exact opposite of how this drawing looks. That's perfectly legitimate on the GRE. They can draw it out of scale. You trust the words, not how big it looks in the picture. And so there we have a direct comparison. Angle POR is the big one. Quantity A is greater. So polygons, any multi-sided figure, and 3 or more sides is a polygon. And of course, some of them have their own special names, right? Triangle is the 3-sided polygon. Rectangles, squares, parallelograms, trapezoids, those are 4-sided polygons. They have other descriptive qualities that we're not going to get into right here, but they are polygons. And one rule about polygons is based on how many sides they have. That determines how big the sum of the interior angles is. So 180 is the sum in a triangle, 360 is the sum in any 4-sided polygon. And the rule for higher numbers of sides is this formula. N minus 2 times 180 is your total there. And so in a regular polygon, like the one shown up here, where all 5 of the angles are the same as labeled, you would just take the sum and then divide by 5. Each angle there would be 180. I'm sorry, obviously not 180. Those aren't straight lines. Each angle would be 108. If you're interested in a way to kind of remember this rule, I find it's easier to remember rules if you kind of know why they exist. Think about splitting any polygon into triangles. So you can split, as we've seen before today, a rectangle into 2 triangles. 2 triangles have 2 times 180 as their total angles. A 5-sided figure can be split into 3 triangles. And that's always going to be the case. If you ever forget the n minus 2 part of this formula, draw a quick test case. So 5 sides, you can draw 3 triangles. A 6-sided figure can be split into 4 triangles, and that's where this rule comes from. 180 times the number of triangles. All right, QC questions, so should be quick, relatively. 1:15 should be your time limit. Pause and think about it and come back. All right, so we have a triangle and a square with the same perimeter. Different shapes, same perimeter. And notice no figure. It's up to you to draw this or envision it, at least in your mind. So you could take an approach where you think about, well, let's just pick a number for the perimeter. 12 is a nice one to use because it's divisible by 3 and 4. So side lengths are easy to get for this square, and you can easily get the area from that. And if it's a triangle and it's equilateral, you could have side lengths of 4. One rule to remember is that an equilateral triangle, the area is always root 3 times that side length. And so in this case, we've shown that b can be greater. But we've made some assumptions as we thought about this. we've made the assumption that the triangle has to be an equilateral. And it turns out that actually is the triangle that will have the maximum area for a given perimeter. So if I went to a right triangle, I can't have the two perpendicular sides equal to 4, because then the hypotenuse would be too long and the perimeter would be too big. So the two perpendicular sides would have to shrink. Any triangle that is not an equilateral is sort of squished. That's the more hand-wavy way of thinking of this. So an equilateral triangle has the most area inside of it for a given perimeter. And actually there's a couple takeaways from this more generally in terms of optimizing area for a given constant perimeter. Imagine yourself with a certain length of flexible fencing. You can enclose the greatest area with that fencing if you don't have any corners at all. A circle will be your best bet. Notice we're focused on the area on the inside. We don't care about wasted space on the outside. Pentagon would be next best of what's listed there. And in general, the more corners that you can make, or the more smooth each corner can be, the better, the more area you enclose. So triangle, among the shapes that you could make, would have the least area. So more sides for a given perimeter, greater area. I would add this second generalization, which is the more regular the shape, the better. And we'll see a better example coming up. So an equilateral triangle will have greater area than some other triangle with that same perimeter. All right, 2 more polygons QC questions. So aim for 2.5 minutes at the most for this set of 2. Pause and come on back. All right, on that first question, both quantities have to do with surface area, just different shapes. Okay, in quantity A, we have a cube. In the other, we have a rectangular solid with different width, length, and heights. And for surface area, it's, do what you would do if you were painting a cube. You paint one side at a time. You figure out surface area one side at a time. Or almost one side at a time. In the cube, you can think about each of the sides. They're all the same, right? So each side has an area of 3 by 3, 9. But there are 6 identical sides, so that kind of cuts down on the math. In a rectangular solid that's different dimensions each way, you have to think about opposite sides. So you have 2 sides, on either side of the solid that are 2 by 3, 2 that are 2 by 4, and 2 that are 3 by 4. And just multiply that out and then sum them up. And the total is 52, so A is still greater. Kind of funny, right? One side shrinks by one unit, one side gets longer by 1 unit, but the surface area does not stay the same. The second question has a straightforward value in one of the quantities. So the action is in figuring out the area of the largest rectangular field that you can fence in by 28 feet of fencing. I think the easiest way to see this is to draw 2 rectangles, right? Making sure that your perimeter is 28. 7 by 7 would do it. 6 by 8 would do it. And notice that the 7 by 7, you cannot make a rectangle that has an area any bigger than that. That is the best you can do. So the rectangle with the greatest area is a square. Think about another extreme example. You could have a 1 by 13 rectangle. That would have a perimeter of 28, but it clearly has a much smaller area, only 13. So the more irregular a shape gets, the more the area shrinks, because you're literally squishing it if the 2 dimensions are unequal. One side gets squished. All right, regular shapes are best for area. Another set, QC and 1 fill-in question. So for this one, your time target should be 3 to 3:15 at the most on the clock for both of them. So take up to 3 and 15 seconds, and then come on back. All right, we've got this hexagon. It's a regular hexagon, which again just means that every side is the same length. It also implies that all of the interior angles are the same angle. Okay, so regular shapes let you label a lot of things. There's a lot of things that are equal. And you could take two different approaches to this one. One is you could actually calculate what those angles are. So we know it's a hexagon, it's got 6 sides. Let's use our n minus 2 times 180 rule. And that means the sum of the angles in the hexagon is 720. So each regular corner in this hexagon, each angle, is going to be 120. And you could look at the picture and see that x and y are each half of one of those interior angles. They're both equal to 60. C's the answer. Another thing you could do is more of a visual approach, and that is to just add another line. If this is a regular hexagon and you split it this way, drawing lines from opposite corner to opposite corner, you create 6 regular triangles within this hexagon. And in a regular triangle, the angles are all 60. So there you go. We'll use that n minus 2 times 180 rule again here at the bottom. We've got 2 different shapes. Y should be pretty straightforward. You know that that's 60 in an equilateral triangle. But you can pull out the rule about 5-sided figures. We've actually done this math before. So 108 minus 60 is 48, and that's your answer. All right, we're going to switch gears a little bit and look at the coordinate plane. So here's the general way that you might be given the equation of a line. In general, if you see x and y in an equation, there's no squared terms or any 1 over x. It's just x and y in normal ways. You could graph that as a line. But most people don't like to graph it when it's in this form. An easier form for graphing is the slope-intercept form. Here it's also called the point slope formula. And that's when you get y equal to mx plus b, where m is just some coefficient and b is just a number. A coefficient is just a number too. So we can solve this line, get it in terms of y, right? Just move over the x terms, divide by -3, and here we are in point slope form. And so the slope is this number, 4 over 3, and the y-intercept is -2. So it's called the point slope formula because you can plot a point, that y-intercept of -2. And then slope is rise over run. So for every 3 that you run over, you're going to go up 4. And that's because the 4 is positive. So if the slope were negative, you'd run over 3 and go down 4. Okay, negative slope means you go down. And with that, you've basically plotted 2 points and you can connect them. So quick and dirty review here. What does various slopes look like? If the slope is 1, your rise is equal to your run. Rise over run equals 1. That means your rise equals your run. And so for every 1 you go over, you go 1 up. You may recognize that as a 45-degree line. Perfect split there. A slope of -1 is just the opposite. For every 1 you go over, you go down 1. -45 degrees. And this is a slope of 1 too. It doesn't have to go through the origin. When slope is greater than 1, your rise is greater than your run. You go up more than you go over. That leads to a steep line. So greater slopes, steeper lines. When your slope is more negative than 1, well, that's kind of like a bigger negative slope. So again, it's a steeper line just going down. More flat lines are those that have slopes that are fractions. Okay, so that can be a negative fraction as we see in this case, or it could be a positive fraction that would go up kind of like that. Parallel lines and perpendicular lines have some slope properties that are really handy to know. So parallel lines are lines that do not intersect ever. In order to do that, they have to stay a certain distance away from each other. They also have to be continuously. And in order to achieve that, they have to have exactly the same slope. So same slope if they're parallel. Perpendicular lines have more of a mathematical relationship that with some calculation required. They have negative reciprocal slope. So what does that mean? If you have one line that has a slope of 2, you take the reciprocal, which is 1 over 2, and you change the sign. Likewise, if you started with a slope of negative 1/2, you change the sign and flip it. Another check, or another way of saying that, is if you multiply those slopes, you should get -1. And that's the case here. All right, let's take a look at this picture, match it up to the equation that describes that graph. Take up to 2 minutes, although I think this could be done in 1 if you are efficient. All right, so one thing that we don't have are actual numbers. We're not told what these points are where this line crosses. So you can't, pinpoint the exact y-intercept. What you can trust from this picture is that the y-intercept is positive. It's above the x-axis. And that gets rid of two of these choices. A and E both have a -2 there. Their y-intercept is a negative. That's not matching up to this graph. So we have positive y-intercept. We also have a negative slope to our line. It just slopes down. Now here's where I think the real GRE probably would have given us some tick marks so that we could accurately say, how negative is that slope? Is this dropping more than it's running, right? How does the rise and the run compare? But for our purposes, we'll just have to eyeball it. So we know we can eliminate choices with a negative y-intercept, that's A and E. We can also eliminate choices that have a positive slope, so that's B, 3/5 is positive. The two remaining choices have negative slope, but they're dramatically different. So a negative 1/5 slope would be a very flat line. It would only drop 1 for every 5 that the line ran over. Very gentle slope there. So since this one looks steep, our negative slope should be expected to be less than -1. And I think you can kind of trust the scale here. Notice that this dimension looks longer than this dimension. All right, here's another coordinate plane question. Take 2 minutes here. Welcome back. Make sure you've got an answer written down. And I know people who can apply formulas when asked a question like this and actually prefer to do it that way. My feeling is if I can draw it, I'm going to go ahead and do that. At the very least, it serves as a visual check of the formula that I'm going to use. And so here, draw it out, right? You've got 2 points. You can plot them. -2, -2. 7, go over 7 and go up 5. There's your point. They want this distance. So anytime you're in the coordinate plane, you can always draw right triangles. And we've done so with these red lines here. So notice that this dimension we know is 9 because it's 2 to get to here and 7 to get to here. 2 plus 7. Likewise, it's 2 to get up to the x-axis and another 5 to get up to the point. That's 7. And at that point, you can just use Pythagorean theorem. That's what the formula is about distance between points on the coordinate plane. If you're memorizing Pythagorean theorem, why memorize a variant of it when you can just draw it and see the right triangle? And when we do that, we square 9, we square 7, add those up, you get 130. And there's no way to reduce that. E is our answer. All right, 2 QC questions about the coordinate plane. Take 2.5 minutes here. There may seem like there's a lot going on here, but there is a shortcut available on at least one of these. So 2.5 minutes, pause the recording and come on back. Okay, so another geometry problem where we're not given a figure on the top there. They just describe some lines. They give us the equation that describes those lines. And we know that we can put it in slope-intercept form. One other clue that we ought to do that is they talk about these lines being perpendicular. Remember what we know. We know that we need to compare the slopes when dealing with perpendicular lines. So putting it in slope-intercept form means we'll be able to do that. All right, the slope of one of those lines times the slope of the other has to equal -1. So putting those both in y equals mx plus b form, you get this. So it's kind of awkward move, right? We've got to subtract the x term. That means it's negative once it moves over here. And divide by d. That means our coefficient is actually this whole thing, minus c over d. Similar scenario over here. You'll have to track negatives in this problem pretty carefully. When we put those two slopes together, multiply them together, those two negatives cancel. So we end up with AC over BD equals -1. That's what we expect. And so you could do the moves from there on out in various ways. Here, I've cross-multiplied just to show that you can rearrange this so that you create quantity A and quantity B in this formula, and it is in fact that they are equal. So if you concluded that they were not equal because maybe you dropped a sign, that was a real possibility. And if you pick D because of that, reasoning that you don't know A, B, C, or D, that would be the right answer if these did not exactly equal the quantities. Now the second one is where the shortcut is possible. In a question about area and that references a figure, get the lay of the land before you dive into calculations. You may or may not need to calculate the area on a QC question. What matters is relative areas, right? So just first look at what shape you're focused on. So A talks about KLMN. That's this diamond, kind of a regular diamond shape. And then quantity B talks about JKLM. Okay, so it's this more irregular shape. But notice that they have a lot in common. The whole bottom half of those two shapes is common. KLM is common to both. And of course, if it's the exact same shape overlaid on itself, it's got the same area. You don't need to calculate it to see that. So this question is really about the top triangles, comparing this triangle to this one that's kind of shifted off to the side. And we've seen this before. Both would be calculated with 1/2 base times height. And here the base is exactly the same. It's that blue line. So this is really a question about the comparison of the height. And quick visual check tells us the height is 5 in both, right? The y coordinate of both of those points is 5. So those are equal too. I don't know what the area is. It would be fun to find out, but you don't need to do that. All right, one graph, 2 questions about it. Take 3 minutes and 15 seconds on these 2 problems. Sure would be nice if you could draw on the screen during the GRE, but you can't. So I do a lot of pointing at the screen, honestly, when I see questions like this, because what you're doing is to find f of -4, you're going to x equals -4 and looking at where the f function is at that point. So we're going to go over 1, 2, 3, 4. We're at -4 here. And the f function is the one that's sort of like a sawtooth. So we go up. This is f of -4. And what's the y value there? It's 2. So f of -4 is 2. So whatever's in the parentheses is your x. F of that x is the y value. All right, similar procedure to find g of -1. So we're looking at these 2 points. Just add up 2 and -4, and the answer should be A. All right, similar logic about pulling values off of the graphs in the second question. The twist there is we've got nested functions. So you always start from the inside out. Just as we started inside those parentheses to know what x value to go to, we're going to do the same thing here. We're going to start with 1. So we're going to go to x equals 1, figure out what g is there. And whatever y value that is, that's going to be the x that we go to next, and then look at the f function. All right, so what points did we use? Color-coded this a little bit. So looking at quantity A, g of 1, we go over to x equals 1. We go to the g function. That gives us a y of -2. So f of -2 is the next step we do. Go to x equals -2, and then see what y is there. It's -2. So notice that what this means is we take an x, we get a y from it. That y becomes the new x that we plug into the second function. That's what's happening. Similar logic, f of 1, we go to x equals 1, we go to f there. That gives us y of 3. That's our new input. G of 3 is right here, and so that equals 0. 0 is greater than -2. Ooh, dreaded VIX. So we've talked about this elsewhere. When you have variables in the answer choices, what can you do? Well, you can struggle with them. In fact, there's a shortcut. So take a moment. Think you can take up to 2 minutes on this one. See if you can do this one with variables, and see if you can come up with a shortcut. Now, if you did this one with variables all the way through, great. You might label things like 180 minus u, using a rule that we've used before today. This angle would be 180 minus v. This corner would be 180 minus u minus v, right? Some of those rules about adding to 180. And then you could just kind of see what comes about. Very inefficient method. So one challenge I would have is, if you worked with algebra, did you finish? A better way to go is to pick some numbers. Now, here you're not free to just pick any old numbers that you want. You gotta pick numbers that make sense, given the rules of geometry. I would add to that, go ahead and make your first pick of numbers sort of match the picture, right? I've picked a u equals 100 that's greater than 90 because that's what that angle looks like. Whatever. V kind of looks like it's about 45. And notice that once I've picked those, I am totally locked in to what that corner angle will be. Has to be 35 because those 3 angles in this triangle have to add to 180. All right, so you can pick S and T, but again, we've got to be mindful that S, T, and 35 have to add up to 180. So I would say, S looks larger than 90. Don't pick 100 again. You want your variables to be different numbers. Just makes it easier to keep track. You're less likely to get wonky results if you've chosen a different number for each variable. Okay, so 95 and 50, they work. And then you just plug them in. See which one gives you something that's true. First one actually checks out to be true. Good practice to plug and just make sure that the others are not true. Okay, and you could do so relatively quickly in some of these cases. In this bottom one, 95 equals, t plus u, we plug in, and that's already too big, so just quit. All right, A is the answer. I love that method. Feels so automatic, and that's what's so beautiful about it. All right, so in a review, the principles are you have to know the rules. You have to. But don't assume the picture is going to let you use those rules unless they give you enough information to tell you, yeah, this picture meets the constraints you need in order to employ the rule. Don't just trust the way the picture looks. And your process is always going to be to draw it. So redraw a diagram given to you or draw, based off of the words. Often with a diagram, they will give you words along with it. So, your picture on paper sort of combines the given information. And from there, look at it and see what rules can I use to label other things. All right, at this point, we're going to do a few optional and advanced problems. If you're pressed for time, feel free to leave the recording playback now. Go ahead and work on your homework. And if you have extra time, come on back and do this part of it. But if you have time now, let's go. All right, here's a problem. Notice that you can select more than one answer. I'll give you 2 minutes on this one, or you can feel free to take up to 2 minutes on this one. I'll pause as you pause the recording. All right, how do we know it's a range problem, except for that big header screaming at us that it's a range problem? Well, we've got an inequality sign given to us. So that says that there's a range of values that will work as opposed to just a single one. Also, kind of the format of the question. You can indicate all answers, not just one. All right, so what do we know? We know the inequality given to us, and we also know what the picture's telling us. So if that is a right angle here, this must be a right angle on the inside, and this is a right triangle. That means M and N have to add up to 90. They ask about the value of N, so go ahead and solve that for N. N equals 90 minus M. Well, what do we know about M? We know that inequality, right? So go ahead and simplify that. And it tells us that M has to be greater than 40. M cannot be 40. If M were 40, N would be 50. But since M has to be greater than 40, N cannot be 50. 50 is not a correct answer, although it is a tempting trap if you lose track of that inequality. It's not greater than or equal to. So a way to kind of do this, this math, you want to have the straightforwardness of being able to do 90 minus 40, but you have to keep track of the fact that it's not exactly 40. So go ahead and use words in there. So 90 minus more than 40 leads to less than 50. If you're subtracting more, you end up at a lower number. Anything less than 50 works, and those are our answers. Triangle picture, fill in the blank, no choices to help you. Take up to 2 minutes on this one, and then come back. All right, first, what are they asking us for? The area of triangle ABC. ABC is the big triangle, and there are 3 little triangles within that. Those are going to be our stepping stones to the big triangle. Does that mean we need to find the area of each of those 4 triangles and then sum them up? Not necessarily, but we can use those small triangles to label as much as we can and then see if we can just, figure out the big triangle directly. All right, so the first thing you might notice is about the angles. There's a few labels given. This is a right angle, which means together x and this angle are 90 degrees. This is a right angle, so this angle is 90 degrees. So we actually have the most information about this small triangle on the right. 90, x, and x are the angle dimensions. Well, if you're saying, yeah, that means, okay, x and x are each 45, you're absolutely right. And it's not much of a leap. If this is 45, we know these two have to add to 90. This is 45. This is already given as 90. This is another 45, 45, 90 triangle. So now we can look actually at these 2 triangles together. We've labeled all the angles. And so notice that it itself is a 45, 45, 90 triangle. And what do we know about 45, 45, 90 triangles? Well, they're half of a square. They're a square cut diagonally. That means equal side lengths. So this vertical line has to be 8. We're really getting somewhere with that. Once you have 8 labeled, you have 10 already. That's a right triangle. hey, it's a 6, 8, 10 right triangle. Even if you didn't see that, you could get this measure of 6 using Pythagorean theorem. So really the key here is getting this labeled as 8. From there, everything else kind of flows. And so if that's the case, now we have the base of the big triangle labeled. We've got the height of the big triangle labeled. And just use that formula. 1/2 base times height. Remember that the base is 6 plus 8. 56 is the answer. And this is the last one in this set. It's kind of a doozy. Take up to 2 minutes on this one. All right, so I said this was a doozy because I could see this being very time consuming. You are given a picture, you're asked about what intersects with it, and they don't ask you just about one thing. Does this line intersect with, this picture? There's 5 things for you to potentially graph. And I think unless you know what graphs of common things look like, the easiest way to do this one is to just graph it. All right, so let's walk through this. You can save a little graphing time if you look at the 2 choices that are most similar. And I think the first choice, A, and the last choice, E, are the most similar. At least they have an x squared. And in that sense, they're kind of like the given function, right? They have an x minus x squared in that one. So it turns out if we plot those, and I've color-coded them here, which you don't have the option to do during the actual GRE. And forgive the waviness of it. That's what it would look like on my paper. That's what they would look like. So the red one, the bottom one, actually does intersect. So if you didn't know that x squared, if y equals x squared, you have this parabola shape. If you didn't know that, how do you get this? Well, do it the old school way. Plug in x equals -2, x equals -1, x equals 0, 1, and 2. And those 5 points alone would be enough for you to get the sense for this U shape. And just notice that the +2 shifts the orange one up 2, and the -4 shifts the red one down by 4. All right, so kind of a nice thing to remember. If you had to draw one of those again, that might speed things along. All right, so far we have one answer that works. The second one is straightforward to draw. It's in y equals mx plus b form. So we have a y-intercept of -2. The purple line crosses here, and it's got a really steep slope, a slope of 7. So we're going to rise 7 for every 1 we go over. And that's a steep line. It definitely intersects here. Another good graph you want to be able to recognize is the absolute value graph. So absolute value basically takes positive numbers and does nothing with them. So if x is positive, the absolute value of x is just x. So in other words, y is x minus 1 in the positive realm. And when x is negative, the absolute value bars turn it positive. So it's like the mirror image right here. If you see a V-shaped graph, it's absolute value. If you don't remember that, again, you could plot a few points and connect them. You'd see that V shape emerge. That one doesn't intersect, not an answer. And f of x equals -2 just means that y equals -2. That's the horizontal line at y equals -2. Doesn't intersect either. So when we put this all together, this is probably what your paper would look like. Try to make it not look crazy or messy. Redraw as necessary. Only 2 answers work. Now I have to say before we close, it's rare to have to draw functions on a graph in order to solve. It's much more likely that you'd have to recognize a graph that's given to you and match it up to an equation, or recognize it as a certain kind of function. All right, but still a nice challenge problem to end with. Good luck with your geometry homework. Make those flashcards. You'll be glad you did.